So hello, everybody. Welcome to the Atto Fridays. Our speaker this week is Dr. Laura Cattaneo from the Max-Planck-Institut of Nuclear Physics in Heidelberg. She completed her PhD in 2011 in experimental physics at the Politecnico di Milano, Italy. And this PhD was dedicated to the fabrication and characterization of different types of nanomaterials, thin films, nanowires, and nanoparticles. And after that, she went to the Radboud University in Nijmegen, the Netherlands, for a postdoc in the spectroscopy of solids and interface from 2011 to 2014. Working on the optical properties of liquid crystals with an international training network project and in collaboration with both academic and industrial partners such as Philips and Merck. In 2014, she started a new postdoc in the group Ultrafast Laser Physics at ETH Zurich, working on dynamical process at the shortest time scales, namely attoseconds in atomic and molecular targets. And since May 2020, she's running her own group named Ultrafast Liquid Crystal Dynamics as an independent Max Planck research group leader at the Max-Planck-Institut in Heidelberg. And she's trying to look at liquid crystals from an ultrafast point of view. And it's a benchmark study to expand towards the soft matter world. And actually, her talk is going to be on liquid crystals, mid-terahertz spectroscopy, and more. So we're going to hear about liquids, crystals, and also more. So please feel free to start. The floor is yours, Laura, and thank you so much for accepting the invitation and for being here today.
Thank you, actually, for the invitation and allowing me to actually give a talk, which is not exactly Atto, but I hope to actually at least move a little bit your curiosity about this new phase and what this material could actually do in the ultrafast timescale. And I will also explain what I intend for ultrafast. And the more in the title is actually, I will not only talk about terahertz, and I will have just a glimpse of Atto even. So the idea is also to touch Atto. In fact, if I go to the main idea and motivation of the ultrafast liquid crystal dynamics group is actually to understand or try to understand the electronic and the nuclear dynamics combined in liquid crystal across a really wide range of timescale. As you see here, I also brought Atto starting from pico. So, but the solid ultrafast timescale, I will consider most of it is from pico down to femtosecond. And across phase transition, which is actually a very important part because this define actually liquid crystals. So on a fundamental level, indeed, I want to understand the line matter interaction across phase transition, and this will ultimately serve as you, Carla, actually said already in my introduction as a model system to start on investigating from the ultrafast point of view and dynamics other materials in the soft matter world, which can touch biological molecules, colloidal system, or again, liquid crystal or organic soft matter material for charge transport applications. And then let's go into the liquid crystal. What is a liquid crystal and why they are so special? And I would like to study them at the ultrafast time scale because actually liquid crystals are a unique system which bridges two phases. They are not a specific material, but there are a class of molecules that presents this phase in between the solid and the liquid phase. And here I'm presenting, for example, how it appears a nematic phase, which is characterized by not a positional order. So the molecule can travel in the bulk everywhere like a normal liquid, but they maintain a long range orientation order, exactly like in a solid. And when you talk about liquid crystal, you cannot avoid to talk about order. In fact, through the definition of an order parameter, which you can see here as S, and it depends on the theta, on this angle theta, which is the angle of that each molecule will actually present in the nematic phase mostly, but in all of their phase, with respect to a main orientation of all the molecules, which normally in liquid crystal is called like director. And from an optical point of view, this is also the optical axis of your system. And then if you compare it with a crystalline or a liquid system, you see that in crystalline, the order parameter is basically equal to 1 because all the molecules are rigidly aligned along one direction. In a liquid, it's basically 0 because all molecules points across all directions and you have all possible values, positive, negative, and the cosine. While in a nematic phase, you have a close to 1 order parameter. And as you see, I mean, liquid crystal is still a liquid, so we'll have fluctuation of such a direction, of such a theta. So also the director will kind of fluctuate, and the normal fluctuation of this optical axis are in the nanosecond time scale on top of the usual hydrodynamics excitation you can have in a simple liquid. So I would like to stress again how liquid crystal look like. From a macroscopic point of view, they look really like liquids, so they form droplets, they are fluid and unable to support shear forces. This is really a picture of a drop of liquid crystal. So, but on the microscopic point of view, they present really high anisotropic properties in terms of optical and electrical properties. And they are arranged in a periodic manner. They self-arrange in a periodic manner, sometimes as a function of temperature, depending on the specific molecule you're going to use. And you can find each of these phases has a different name, but let's see what it means actually. Nematics means that all the molecules normally are elongated molecules. This is why they are indicated by these cigars. They don't have positional order, but only orientation order. So all molecules are oriented along a main axis, which is again the director. But you can increase the degree of hierarchy of the structure, and you can go to a smectic phase. This is called smectic A phase, where all the molecules are subdivided not only along a single direction, but in layers. So they have also sort of positional order. And if the molecule within the layers has a certain tilt, you get to different and more exotic smectic phase. You can have chiral phases, or you can have even extreme chiral phases, which will allow to have three-dimensional orientation of defects actually in liquid crystal. Or you can have also disc-like molecules. In fact, they are called discotic and forms columns. They reorder in columns. And in fact, they form a columnar phase. In this talk, I will mainly talk on two different liquid crystals. Here you can see it on the left. They are the most commonly commercially available liquid crystal. So this is a 5-cyano-biphenyl. C stands for cyano and biphenyl. The cyano group, you find it here, nitrogen and carbon. And then you find the 2-biphenyl ring. And attached you have a alkyl chain, and 5 stands in fact for the 5 carbon atoms. And 8 here is exactly the same, simply it has 8 carbons in the tail. And just adding these 3 more carbon atoms, you get an extra phase in between the nematic and the isotropic. Here we are talking about thermotropic liquid crystal. Means that you can have a phase, you can actually induce phase transition by applying temperature, by giving temperature to your system, to increasing the temperature of the system. And then in the 5CV, you pass from a solid to nematic to isotropic, and isotropic means liquid. Actually, in liquid crystal, the isotropic phase is further subdivided in kind of other phases, because right after the transition, the liquid crystal still remembers to be a liquid crystal. So to have a real liquid phase, you have to go much higher than 35. You have even to double it. And with this HCB, you get actually extra phase, which is the symmetric eye. Now I want to show you how it looks like a phase transition under a polarizing microscope. The colors are not real, because there is a specific plate inserted in the microscope just to make it more easy to see. And here you see the passage from nematic to isotropic. While here you see the passage from symmetric to nematic, which is more subtle. You see now it's coming. It comes from a very smooth surface to now you can see actually the scratches on the substrates that contains the liquid crystal. So it gets towards a more liquid phase. And now comes the question, where do you see ultrafast in all this? Well, I didn't show you at all ultrafast. This all happens in seconds, actually, or even longer. But I want to actually guide you in a sort of a journey from millisecond up to kind of attosecond, and convince you that liquid crystal could be an interesting material to be studied in the ultra-fast time scale. So liquid crystal normally are used in liquid crystal display, exactly where you are looking into. And they perform what? Movement and an entire rearrangement of the molecular axis due to the application of an external voltage. And this happens in the millisecond time scale. Then, back in the 80s, when the liquid crystal had their boom for the application in liquid crystal display, many groups decided also to try out many other things on liquid crystal, not only voltage application and new synthesis to have best performances of liquid crystal, but at that time they actually tried to shoot nanosecond laser into liquid crystal, and they could observe temperature-induced dynamics into the microsecond time scale, micro to nano actually. The resolution was what they actually surely saw was, for example, the fluorescence activity of liquid crystal, which falls into the in the 400 nanometer more or less. And this change that you see here depends how much diluted they dilute the system from having a liquid crystal system, which is the molecule I showed you are not diluted in a solvent. So a liquid crystal is purely monomolecular system. So they are composed by only the same molecule, and they are liquid like water, okay? So they are not diluted in anything, but if you dilute them, you might actually want to highlight the single molecule behavior. Or if you actually have the neat liquid crystal, you get actually most of the excimer response, because liquid crystal tend to form excited dimer. So when they get excited, they form dimer facing the two biphenyl groups, one in front of the other, and having the tails either along the same direction or in the opposite direction. And I explain this because this might be also an interesting point to actually go for faster investigation about this. They also, in 2013, actually, they also demonstrated for the first time the possibility to modulate the refractive index of a liquid crystal, which normally is done by turning the molecules like in the millisecond, like you do in a liquid crystal cell and display, but in the nanosecond time scale, and still applying a voltage. And in fact, what they observed was almost an instantaneous response, at least when they applied the voltage. And it was mostly limited by the instrumentation that they were using in order to acquire this measurement. And this was one of the work that actually started to inspire me towards the ultrafast investigation of liquid crystal. And then we end up in the picosecond time scale. This is the typical time scale where you have vibration. And in fact, back already in the 80s, they observed that by, for example, triggering liquid crystal with an 800 nanometer pulse around 2 to 300 femtosecond time scale, they could actually excite what they consider instantaneously the electronic part back then. But then they had an almost instantaneous 2 picosecond for the Atto community. This is infinite time, but for such a molecule, this is really fast. So this nuclear activity thermalizing within 2 picoseconds right after the interaction with the light pulse. Fallout with the name, they name it librations. What are librations? This is not only in liquid crystal, this is common in liquids to have libration, which is a combination of rotation and translation of the molecule. And then if you convert it, so now this is a time domain measurement, but if you convert it in the frequency domain, and in fact, recently it has been performed an absorption measurement in the same, what is actually now kind of famous terahertz frequency domain, we can observe that indeed in the 1 to 5 terahertz or 1 to 6 terahertz, we have an activity, a huge activity of liquid crystal. This is absorption. And what is stand for ordinary and extraordinary is the relative orientation of the polarization axis of the terahertz pulse with respect to the main axis of the molecule, which sees the extraordinary refractive index of the system, or across or against the liquid crystal orientation and sees the ordinary axis of the system. And here indeed, I also, in the same time, I perform my self-measurement, simply hitting with a 800 nanometer under femtosecond pulse on a 5 CB liquid crystal, so the nematic phase, and probing simply how the interaction with the trigger liquid crystal would actually modify the polarization axis of my probe. This is actually a time-resolved birefringence measurement. And what you see here is the transmission and the relative reorientation of the polarization axis. I would actually concentrate on this. Actually, if we start on the transmission, here you see the double kink that stand for the electronic and the nuclear part, exactly as what I showed you before. And the rotation here actually can be translated in a modulation of the refractive index of your material, and is modulated indeed in the terahertz frequency domain. But to give you a little bit of an idea, what is a libration for these molecules, I will use actually some calculation that has been done by a collaborator, but in the gas phase. So considering a single molecule, which is not exactly the real life in a liquid crystal. And here you see the comparisons exactly from, they kind of match, but they are not exactly the one. And so my place is to understand what's the difference when you pass from the gas phase to the real liquid crystal world. But here, for example, are the type of dynamics we think they could actually undergo at 2 terahertz here and 4 terahertz here for the 5 CB and 8 CB. And as you can see, is actually extremely, the entire molecule actually is moving. It's not only a single part or a single bond, this is all the molecule. And then you have to picture that in a liquid crystal, all the molecules will move together in the same way because they are aligned. And there is a long range elastic order that will actually bound them together. So this is my main motivation in studying liquid crystal in the terahertz frequency domain. And to do that, time resolved, indeed in the lab, we build up a terahertz setup that I will show you in a bit. And probing indeed the birefringence, the induced birefringence by the terahertz interaction. And this will give us a macroscopic idea of what's going on in a liquid crystal in terms of intra and intermolecular dynamics, and somehow the relaxation path that the liquid crystal will go into. And in case if we have any phase transition going on while the terahertz is impinging, because we can actually also change the knob of our temperature while we are measuring and have actually an idea of what is going on. And in order to have a microscopic idea of what is going on, we actually also go for not only an optical observation, but also an X-ray diffraction observation in order to see exactly at the molecular level what is going on. And then let's concentrate on the first part. And here, before starting with the core of the measurement that I will show you, I will introduce a little bit the terahertz radiation, because I don't know how familiar you are. Since me too, coming from the attosecond community, I didn't know that much about terahertz, and I'm actually starting since 2020 to know it. And indeed, it's a frequency that lies between microwave and infrared. And you cannot see it, absolutely, but this is not really a problem. And it actually lies in this region where you have a micrometer, hundreds of micrometer wavelength. And it's actually not strictly defined, because if you see, most of the papers can declare different areas of the infrared spectrum and still claim it to be terahertz, but the general understanding is that it goes from 0.1 to about 10 terahertz. And indeed, the energy. So let's talk about energy, since we are in the attosecond community here. It's completely different from the usual few to 10 to electron volts. We are in the milli electron volts, so is equivalent to a thermal excitation of our system. Okay, so then what happens? What happens normally in the terahertz frequency range? What you can excite in using this wavelength? Actually, rotation and of molecules, or large amplitude vibration, like I showed you right now. Lattice vibration means phonons. Phonons are the classic in condensed matter to be excited via terahertz, or intravent transition in semiconductor, or the so-called magnons, so this delocalized spin wave into magnetic materials. And here is the setup that we actually built here at the Max-Planck. So the red indeed is the near infrared that we use to generate terahertz via optical rectification in a nonlinear crystal that sits here, is green. It's called the STMS. Don't ask me the real name because it's extremely difficult. And then here we have the green stands for the terahertz beam that actually perform 3 foci. And in this line, we can characterize our terahertz beam via electro-optical sampling using, again, another nonlinear crystal, which in our case is most of the time gallium phosphide. And here, oops, it went too fast. And here instead we have our probe beam that you see. It's since here we are not using a whole parabolic mirror to get straight, we are performing this zigzag movement with some pellicles, and we do actually the same type of detection we do to extract the terahertz field. The time trace of the terahertz field that we can convert then in frequency by simply performing a Fourier transform, windowing, as long as we don't see replicas of the field because of the surface at the gallium phosphide that we use to actually measure it. And as you see, we can, via the optical rectification with this specific organic crystal, we can cover a range between 1 and kind of 5 terahertz or 4.5 terahertz. And here is how we expose the liquid crystal to the system. So the liquid crystal is sandwiched by 2 glasses. Actually, we don't use real glass because glass is not good at the terahertz radiation. We normally use silicon carbide. And here we use a temperature control system in order to perform in a controlled manner phase transition into liquid crystal. And we can actually perform time static measurements of simple absorption of the liquid crystal. How? Well, actually, you see, this is our time trace of the terahertz in the reference cell with no liquid crystal. And as soon as we put liquid crystal, the terahertz field in the time trace, this is exactly how we measure, will actually be moved in time, obviously. But also the frequency components will change. As you see here, there are some difference in how the pulse looks like. And then we can extract indeed from the Fourier transform how it looks like. And from differentiating, it comes how we can exactly extract the absorbance measurement that has been already and confirm from the previous picture that I showed you already of the absorption of 5 CB, for example. This is the ordinary, the black, and the extraordinary is the red. And here is the relative orientation with respect to the terahertz polarization axis. And we nicely reproduce the peak at 4 terahertz roughly in the ordinary, and the small kink and the extraordinary. And here we go directly to the time resolved by refringence. So let me introduce first. These are measurements that have been taken last week. So literally last week. So our interpretation is still hand waving in the sense that we are still trying to understand what's going on in the liquid crystal. And so let's start from the left. So these are the conditions at which this curve has been taken. So pump and probe are along the same polarization axis, while the liquid crystal are showing their ordinary axis, so in cross orientation. We are actually studying 8 CB, and here you see we perform all these plots are as a function of temperature, meaning that we are going from the solid, because it's 15 degrees, what is, can be considered solid phase, to the smatic at 25, 35 we have pneumatic, and then 45 and 70, 45 is the isotropic, still remembering to be a liquid crystal, so presenting what is called the quasi-pneumatic domain, and 70 degree is exactly liquid, what we expect liquid. So we can see different behavior as a function of temperature, clearly. We were expecting actually much higher modulation on top of a general, let's say, pedestal or positive response in a way of chiroptical effect. And this is why my interpretation will not try to be more deeper, because we are not sure we are free from artifacts here, because unfortunately, when you work in the terahertz frequency, as I got to learn, you are suffering extremely from multiple reflection at each interface you actually expose to it. And here we have many interfaces. We have the first silicon carbide, because this is silicon carbide, which has been chosen exactly not to present any absorption in the terahertz, which is also not easy to find materials that are so very suitable for it and still able to contain a liquid. And then we have the surface between the silicon carbide and the liquid crystal, and so on. So we think that we are washing out features here, but at least I could show you that there is a clear signal, first of all, and there is a dependency on temperature, which we'll have to elucidate in a more detailed way. I have also another set of measurements that I would like to show, still same HCB and still temperature dependent. So I'm showing you in blue the smatic, in orange the pneumatic, and at 70 the clear isotropic. And what's the difference here? We actually are picturing our system still pumped in cross condition with liquid crystal, but observing our observable, so the probe is at 45. So it's having also an eye on the long axis of the molecule, so the extraordinary axis. And this makes the liquid phase to appear extremely much slowed. Also, if we see actually how slowed in a sense that the relaxation seems to appear much later, but the first response is much faster, while the other two seems to be slower, and it goes with temperature indeed. Makes sense. But then why this trend to actually lower or increase, this has to be still analyzed actually. So these are really, really fresh results. And another, so I also, when I introduced how we intended to study liquid crystal in the Therards time domain, I said that we would actually like to study them in the with optical observation, but also in the X-ray frequency or X-ray wavelengths. And then we use X-ray scattering, and this is our preparation work to a beam time we will have in a few weeks, the European XFEL, where we will only pump with a 800 nanometer pulse because Therards is not available at the moment. But still, the 800 nanometer will induce some dynamics. So we hope to be able to have a detailed idea at the the molecular level, what is going on, and the preparation work required to expose liquid crystal not contained in anything. So then all this big thing you see here is a holder that allows to have in this hole a freestanding liquid crystal film, because HCB allows to have freestanding film. And this part here is actually a wiper that goes up and down. And here we have a reservoir of liquid crystal, which provide outcoming liquid crystal in order to have fresh surfaces on demand. And how the liquid crystal align into the film, we say homeotropically, means that the molecules are perpendicularly aligned to the surface of the film. And here I have a little movie to show you how it works. So you clearly see the film, and it has a very precise orientation. And here we are breaking the film. So you see that it's disappearing. And you can imagine like the same type of film you have when you have soap bubble, except that we don't blow them actually. And we have them there, and then we try to study them in this configuration. And at the same time, I would like to show you, this is how it looked like closely in the microscope. And we are performing here an increase of temperature. This is why it's all copper, and this is temperature sensor. And then we are going into from the static to the nematic phase. So you will see, so all this is where the liquid crystal is trying to accommodate for different thicknesses. And now we have a full phase transition. And still the film is withstanding the phase transition, which actually was surprising, and we were happy about this. And here indeed we have the first measurement of yesterday night, where we actually are scattering X-ray from the freestanding film in reflection. So we don't have right now the IR, of course. And then what you see here is the first order diffraction and the second order diffraction, standing for the layering of HCB. And here you can see in this model where the molecules are actually simply converted into balls and different colors, that the layers, one layer is not just one molecule, but are two molecules facing the tails to each other, and then having the other, the biphenyl, the cyanobiphenyl group all together. And then basically one film is two molecule pairs up, and it's actually measured about 3 to 3.1 nanometer. And this is exactly what we are trying to establish in static, and then to actually then access in dynamic way in 3-4 weeks. So I hope to have the possibility to talk to you again about the dynamics of this. Can we go faster actually? So I would like to try in the last 5 to 8 minutes to actually get you that a little bit of even faster activity. What can happen in the femtosecond time scale? So the ultimate goal of what I'm researching is the fact that due to the fact that the liquid crystal like to form excimers or excited dimers, there might be the possibility to promote exciton formation and have localized charge transfer as soon as the conditions are allowed. And which are the conditions? It actually really pretty much depends on the distance between the two cyanobiphenoid groups that are facing to each other in order that this can happen. And one tool that we can use in order to induce the change of the relative distance between these molecules could be the terahertz electric field that we apply temporarily. And then for electron, this is an infinite time where charge transfer actually can happen. And this would be actually the ultimate goal. And how I'm going to detect this at some point would be via high harmonic generation. And this is where the Atto second comes. And so first we need to demonstrate before combining terahertz and high harmonic generation to actually access the high harmonic generation effect in liquid crystal, which has never been tried. So this is mostly the why we want to do it for a self-probing, as a self-probing mechanism, not just to have harmonic generation per se. And this requires, I don't have anything to show you, but because it requires some technical works in the beginning in order to, again, expose the liquid crystal to such a high intensity, to a strong field in this condition, and expose constantly a fresh sample to the field. And then we actually had to come up with a flat jet solution. And right now there is a bachelor student working on it, extremely motivated because he actually made a first demo out of a 3D printing setup. But that unfortunately, obviously work only with water. And here you see a picture in water, but now we are scaling up everything for liquid crystal, which is by definition a viscous liquid. So it allows a completely different dynamics and it requires much more strong pumps and it will actually present completely different regimes in which to have this flat jet. So I hope next time to show you some results, because on top of it, we will need to actually temperature control the system in order to allow a specific phase to be present in this flat jet, which will also impose, because of the flow and because of the long range elastic order of the liquid crystal, a specific alignment into this flat jet. And the idea indeed is to expose it to a mid-infrared pulse to have high harmonic generation in the visible spectrum to avoid for the moment vacuum. Although liquid crystal can withstand vacuum, but there are so many other parameters to control at first that vacuum will all complicate the picture. So with that, actually, I would like to get to the take-home messages. So the road so far at the ultrafast liquid crystal dynamics included a static characterization in terahertz, and we are performing now all the dynamic investigation in order to have an idea what's going on when you impinge with a strong or intense terahertz pulse. Most probably I didn't mention we can actually at the moment get to up to 500 kilovolt centimeters. So you estimate the intensity of your terahertz pulse with the voltage that you can get into your field. But we want to at least double it in order to see if there is any regime where we can actually induce nonlinear effects. And then we are trying to develop all the other technical aspects in order to increase our level of understanding, also the microscopical point of view, and in the Atto second, and many other ideas on the way, given the fact that the liquid crystal world is really huge. And with that, I would like to thank my group, which is currently composed by Max, working on the flat jet, Marius and Patri. They are currently measuring the Petra, and they are also responsible for the terahertz measurement, and Elias on the huge holder you saw for the freestanding film. I would like to thank also my former members, the technical and electrical workshop and the Max-Planck, which are a huge support, and of course, you for your attention.
So thank you so much for this really nice talk. Are there questions, comments? Andre Stauze, great presentation, very challenging work. Good luck with that. And there is the email.
Andre, okay. Thank you. Yes. Thanks, Andre.
Yeah, and we have a question from Andrea Annunziata. Can the interface with the glass change the orientation of the liquid crystals?
Can they?
Can the interface with the glass change the orientation of the liquid crystals?
Yes, of course. I mean, we use the interface with the glass to impose a specific orientation of the liquid crystal. So there are different ways to impose, for example, let me get to a specific slides. Can I? Yes. So if I go here or here, that's better here. We have different processes, if you can see. In order to impose a specific orientation on the glass, we actually take the glass. Ooh, I cannot hear anything.
I was referring to another fact in the sense that if the liquid crystal close to the interface can be oriented differently with respect to the liquid crystal inside, let's say, the bulk. If the interface itself, the glass itself,
sorry, it's really difficult to understand.
Yeah, it was difficult to understand. I think there was some interference.
I could actually understand that he was talking about the bulk and the surface, if there is something different. So if the glass by itself can induce a reorientation of the liquid crystal with respect to the bulk. Okay, I will try to reply. So we modify the surface. So liquid crystals are not in contact with the surface of the glass, but we cover the glass with a polymer. And this polymer is afterwards rubbed in a certain direction in order to actually impose a planar alignment in a specific direction. And this, due to the elastic long order orientation of the liquid crystal, will actually be maintained in micrometer distances. So only we see that this way to impose an orientation fails when we go over 100 microns. So if you go over 100 microns in thickness of the liquid crystal cell, which is huge, we see that the center, so what is sandwiching at the center, will not still feel the imposition from the surfaces. And then you use electric field. You put electrodes, you apply a voltage, they are polar molecules, they reorient, and then you can impose across many order of magnitude in thickness the same orientation. And then you can tune it, by the way. With the voltage, you can tune it.
Okay, thank you.
Yeah, we made it. I think we made it.
Yeah, we're fine. Thank you for asking.
I can also announce that I'm looking for PhDs. So if there is anybody in the audience that would like to actually ask a question or interested, just let me know.
Exactly. Drop her an email and she'll be ready to reply to you in any case. And it was a really interesting talk. If there are no further questions, I would like to thank everybody for joining today. I would like to thank the speaker as well for this wonderful talk. And for those of you who are watching on YouTube, have a great weekend. And we see you in 2 weeks. And thanks for supporting us. So take care, everyone.
Thank you. Bye. Have a nice
Bye.
weekend.
Thank you.